Good morning, everyone. It's my pleasure to present our work, Robust Data-Driven Predictive Control using Reachability Analysis. Cyber-physical systems are becoming too complex to model. One often has a lot of data, but no model to guarantee safety. For example, consider this arm robot, where it's very difficult to model and control. Consider this dog robot, which was in the news recently, and it goes through different environments, and the task is to control such dog robot regardless of the environment and achieve all the required tasks of the dog robot. This leads to the following problem formulation. If we have a black box embedded system and we have the input and we have the output, can we design a data-driven controller? The big picture behind our paper is as follows. We don't have the robot model. Instead, we compute a set of models consistent with the data and the noise bound. We guarantee that the true model is inside the set of models. And we predict ahead using the set of models computed from data. And we find a controller such that the output stay within the reachable region computed from the set of models. So we have input data, input output data, set of models computed from the data, and we compute the reachable region out of the set of models, and we find the controller such that the output stay within the reachable region. I have divided my talk into 3 small parts. First, I will talk about basic reachability and some set representation properties, then how to predict ahead, then how to formalize the optimization problem. So let's start. As a set representation, I'm using Zonotopes, which consists of a center and list of generator vectors. So the center is added with beta from -1 to 1 multiplied by the generator. And we have the center added to G1 plus minus as shown here. If we add another generator, we will have this shape. If we add a horizontal generator, we will have this shape. So we can build and construct complex shapes using Zonotopes. Also, a matrix Zonotope consists of a center matrix and list of generator matrices instead of vector center and vector generator vectors. Zonotopes have nice properties that allow to do complex operations using simple computations. For example, we can do linear map by multiplying the center by L and the generator by L. We can do Minkowski sum, which means adding each point from the first Zonotope to each point to the second Zonotope. Can be computed easily by adding the centers and combining the generators. Also, Cartesian product, which means vertically align all the Zonotopes, all the points from the first Zonotope to all the points to the second Zonotope, can be computed easily by vertically align the centers and having the generators as shown here. These nice properties qualify the Zonotopes for an easy model-based time update. Consider a system where we have xk plus 1 equal ax plus bu, and we have the C matrix as identity, which is the output matrix. So we will have yk plus 1 equal the following. And to compute the reachable region for y, we will have the model multiplied by the Cartesian product between the reachable region and the control input, Minkowski sum, the noise Zonotopes. We assume the noise is bounded, but we don't assume a distribution for the noise. Next, we will see how to predict ahead. So how to predict ahead in our data-driven controller. The proposed approach can be summarized in the following. Given the noisy data, there is no single model that can be trusted and fits the data. Instead, we compute a set of models consistent with the data instead of depending on a single model. And we guarantee that the true model is inside the set of models. And we propagate ahead and have the time update starting from the initial set or the current set. And we propagate using the set of models to compute an over-approximation for the reachable set. Let's define the set of models. We have the noisy input-output data, and we have set of models that's called N sigma, which contains the true model inside. So it's all the A's and B's that satisfy the data and the input that satisfies the data and the noise zonotopes. First step is the computation of over-approximate set of models. The idea is the following. We have a bounded noise, which is a matrix zonotope contains all the matrices, the noise matrices, and we move along all the possible values of the noise, and we compute a corresponding set that have all the possible values of the model and will over-approximate the defined set of models. So we will have from system model the data and the noise as showing here. We don't know the A and B, so we will have it on one hand and the left-hand side, and we don't know the true noise realization. So we will represent them as a single point, unknown point inside the matrix zonotope MW, MV, and MAV, multiplied by the pseudo inverse of the data. And then we move along all the possible values of the noise, and then this will lead to M sigma, which contains all the model in N sigma, and consider over-approximation for the set of models. Then we propagate ahead, and instead of propagating ahead in case of model based by multiplying by the model, we will propagate ahead by multiplying by the set of models as shown here. Next, we will find the controller and formalize the optimization problem. We find a controller such that the output stays within the reachable region. So we have the set of models and we compute the reachable region using the set of models, and we find the controller subject to output stay within the reachable region and have some input constraint, output constraint, and bounded noise. And this is a formulation with some slack variables to tighten the constraint and have robust constraint satisfaction. Consider the reachable region as shown here, and we have the output constraint here. We will have the slack variable to do the following job. Consider the simulated output here. However, the true output may be any point towards the upper bound, for example, in worst case. So we compute a slack variable R minus Y, which is this value. And then we tighten the constraint. So we choose the output such that the constraint is tightened by such a slack variable. By doing this, we guarantee that the true output is still satisfy the constraint. If we don't have the slack variables and just say the output stay within the reachable region, we cannot guarantee that the output or the true output satisfy the output constraints and the input constraints. That's why we have the slack variables. This is a system, and we have the simulated system and the reachable region the true trajectory is within the reachable region as shown here. And we compare against robust MBC using polytopes and compare against RMBC Zono, which is our proposed approach ZBC, while passing the model to it. As you can see, they are competing and the output is close to each other, and we have robust guarantee satisfaction, while ZBC is more conservative because of the constraint tightening. Then we increase the noise to 10x to qualify the differences. As you can see, there is more error in ZBC because of the noise, which is expected because it's a data-driven controller. And we have a more conservative constraint tightening here. So this is the constraint, and we are ZBC is above. I acknowledge my co-authors and appreciate their efforts and support. We have computed data-driven controller using reachability analysis with formal guarantees. We have computed set of models that's consistent with the data, and we find a controller such that the output stay within the reachable region. This is my website and the reboot to regenerate our findings. Thank you so much.